So this is part 2 of the video for Lewis structures. We left off in part 1 talking about multiple bonds in molecules and got into some pretty complicated non-conforming molecules based upon what you learned first year. There is another way that you can work out the bonding scheme of molecules that have octets at least. So this is a computational approach. So what you're going to do, this first slide goes through the steps, and then I've got some examples to show you. So you're going to add up the valence electrons in all the atoms of the molecule that you actually have. So how many valence electrons are actually there? Then you want to figure out how many valence electrons you need in order for all the elements to achieve that noble gas configuration. So hydrogen needs 2, every other element needs 8. And then what you're going to do is subtract. You're going to calculate the difference, the need, what the have is, because you always need more than what you have since you're making bonds. And then that difference really represents the number of shared electrons that the molecule has to have. Well, since a bond is 2 electrons, you divide that number by 2 in order to get the number of bonds that you're going to need. So it's always easier to see an example. So the next slide has an example. So let's say we want to do oxygen. Okay, we'll keep it simple. I know you know that we need a double bond. So we've got oxygen. Each oxygen has 6 electrons, so we have a total of 12. We need 8. Each one needs an octet, so we need 16. Well, the difference between that is 4, so we need to share 4 electrons, which means we need 2 bonds. So we're going to put the double bond between the 2 oxygens, and then we're going to fill in the rest. So after you build the basic skeleton, which is what we have here, you want to add the remaining electrons in order to complete the octet, and then you want to double check. So there's 2, 4. Remember that we have to use 12 electrons, so we've already used 4, which means we have 8 more left. So we're going to put 5, 6, 7, 8, 9, 10, 11, 12. So we've got all 12 electrons accounted for, but we have 16 essentially bonded because we've got 2, 4, 6, 8 for one oxygen, and then 2, 4, 6, 8 for the other oxygen. One more example, we've got carbon monoxide. Again, remember that has that triple bond, and here's how you can prove that that's what you need. So carbon needs 4, oxygen needs 6 for a total of 10. I'm sorry, it has that many. We need 8 each, so we need 16. So 6 electrons have to be shared, which means 3 bonds. So what are we going to do? We're going to put that triple bond in between. That accounts for 6 electrons. We've got a total of 10, so that's 4 left. I'm going to put 2 on one side and 2 on the other. Once again, 2, 4, 6, 8 accounted for, 2, 4, 6, 8 accounted for. There is our structure. So you're going to figure out how many electrons do you have to work with, how many electrons do you need represented. The difference is going to tell you how many shared electrons have to be there. You divide that number by 2 to figure out your number of bonds. So just some general hints for Lewis structures. These are things that we've gone through before. If a given molecule can be drawn both symmetrically and asymmetrically, you're going to go with the symmetrical one. It's more likely to be there. Remember that central atom is often written first in the formula, or it's the least electronegative element, or what we learned last year, it's the element that can form the most bonds. So carbon always winds up being our center atom because it needs 4 bonds. Remember that hydrogen halogens can only form 1 bond, so they're going to be at the ends or terminal atoms. In general, you can interchange all these. So all the halogens and hydrogens you can kind of pluck in and out, and it doesn't really change your structure at all. And then elements in the same family you can always substitute in for each other. So nitrogen, phosphorus, or AS is arsenic, I think. You can always, anything in the same family is going to behave the same way in terms of bonding schemes. All right, so let's take a look at some exceptions to octet rules. This is probably going to rock your world a little bit, and maybe not in a good way. So remember we said most of the atoms are going to have octets when they finally finish bonding, because that's what makes them most stable. However, do remember that when we were looking at some of the metals that actually form bonds, you don't have to have 8. So what we did with the first 2 columns, we wanted to just pair up those unpaired electrons. So something like lithium is happy just forming a single bond and having 2 electrons in its valence shell. Group 2 elements, the alkali earth metals, will do 4 electrons, and then the aluminum boron group will do 6 electrons for 3 bonds. So there's one exception that we saw last year. One of the other things that we did not see last year, and this is the part where your world is going to be a little uncomfortable for a few minutes, is the fact that you got to remember that elements in period 3 and beyond have unfilled d orbitals, which actually are going to allow us to exceed the octet rule. So we're going to use some d orbitals to help us with bonding in some cases. So how does that work? So typically when you have a number of electrons in an atom that exceeds the octet, what's going to happen is a pair or more than a pair of electrons is going to, around the central bond, it's going to split, and one of those electrons is going to occupy a d orbital. So let's go take a look at some examples. I'm going to take a very quick moment and write them down so I don't forget what they are. And then we're going to take a look at some of these examples. So hang tight till I switch over screens. All right, so what we want to take a look at is how the heck does PCl5 happen? Because if you remember, P is supposed to have 5 valence electrons. So it would make sense that each chlorine would bond with one of those electrons for a total of 3, because this pair of electrons is already filled up. Well, what's going to happen is this non-bonding pair is actually going to split apart. And one of these electrons is going to stay in the P sublevel. One of them is going to go to the D sublevel. So that's where you can have the rest of the chlorines bond in. So each chlorine, remember, has 7 electrons. So there, the bond is its 8th. And you wind up with 5 single bonds around phosphorus. This is absolutely a true substance. 5 single bonds because you've got, the S, the P, the P, the P, and now we have a D orbital represented. So anything above group 3 has an entirely empty D sublevel that can be used for bonding, and that's what's going to happen. One of these P electrons is promoted. Notice that it completely skips an S sublevel in a higher shell. It stays in that same principal energy level and gives you a D orbital for bonding. So the same idea is going to happen with bromine. Normally, we've got the 7 electrons around bromine, which only one of them is unpaired. So it should only bond with 1 iodine. But we've got 3 iodines to deal with. So similar to phosphorus, one of these pairs is going to split, and you're going to get iodine forming bonds with it and its lone electron and the 2 that we split. So again, one of these coming from the P and going to the D. Xenon, a noble gas. Here's another freaky thing. You've got xenon with its full octet, yet you can have xenon forming bonds. So here again, what's xenon going to do? It's going to break up its pair, and it's going to form single bonds with fluorine. Something like that. All right, so yes, it is possible. I am not lying to you. You got to be a little more open-minded. But again, one of the electrons from the normal sp area is going to get promoted to a d, and so then we have more single electrons than what we normally thought we would, and that's how we can get the higher order bonds. And we'll take a look at what kind of shapes you get as a result of all this as we move ahead. All right, so moving back now to the PowerPoint. So we've done those 3 examples. You've got a chance to see. We're going to move on now and take a look at the idea of formal charge, but I'm looking at my time and I'm at 10.5 minutes, and so I think we're just going to do part 3 for formal charge. Formal charge is another way that you can figure out what the Lewis structure, what the most likely Lewis structure is going to be. So go to part 3 and we will pick up formal charge there.